Okay, in example 2, we revisit our previous radio-controlled model car, but in this case, you'll see that the velocity along the x-axis is changing, and on the y-axis actually it looks like it's not changing. So this example, we have an acceleration occurring. If you can imagine, look at this velocity at point 1. Instead of plotting out the position, we see an xy coordinate system drawn here, but what we're showing now is just the velocity vector. So this is the velocity of the remote control car at point 1 along the x-axis is moving 1 meter per second, and along the y-axis is moving 3 meters per second. If you were to draw a parallelogram, you could show that what this velocity v1 is as a resultant. And then we could do a similar thing for the position 2. And there we have velocity 2. And you could see velocity 1 and velocity 2 are not in the same direction. In fact, it's getting faster as well. In fact, since the velocity is changing direction and also magnitude, the particle is moving in a curved path, something like this. And so the velocity at point 2 is the velocity that is tangent to this curved path. So this is the actual path of the object. It's actually following a nice curved path. In the previous example, example 1, we were dealing with a remote control car that was going in a straight line at a constant velocity. The reason why the object is moving along a curved path is because the object is accelerating, and that's what we're trying to find in this problem. We're asked to find the components of the acceleration along the x and y axes and the magnitude and direction of the average acceleration during this time interval. So if you recall, the definition for acceleration is the change in velocity over the change in time. Now that we're looking at an object moving in two-dimensional motion, we can break up that acceleration along its x and y direction. So let's find the acceleration along the x-axis, which would be the change in velocity along the x-axis divided by time. And let's find the acceleration along the y-axis, which is the change in velocity along the y-axis divided by the time. So to find the components of the average acceleration along the x and y-axes, we're going to need to find the change in velocity along the x-axis and the change in velocity along the y-axis. So we know at point 2, the horizontal velocity is 4 meters per second, finally. And then initially it was only 1 meter per second. So we're going to take the difference between those two numbers, divided by the time interval, 2.5 seconds and 1 second. So 2.5 seconds minus 2 seconds, right? And so you will get 3 meters per second on top and 0.5 seconds. So this will give you an answer of 6 meters per second or meters per second squared horizontally. So it's accelerating horizontally to the right with an acceleration of 6 meters per second squared. Along the y-axis, we have a final velocity of 3 meters per second, and then an initial horizontal or vertical velocity of also 3 meters per second. So vertically, it doesn't matter what you divide by in time interval, you're actually having no change. So 0 meters per second over 0.5 seconds or 0 meters per second. So it's not accelerating along the y-axis. We only have acceleration along the x-axis of 6 meters per second squared. So let's go on to part B. We're trying to find the net average acceleration. And that you can think of as if we had two accelerations, if we had an acceleration along the x-axis and we happen to have an acceleration along the y-axis, then to find the acceleration as a resultant, you would just use Pythagorean theorem, ax squared, the horizontal component, plus the y component squared. But it turns out that you have 6 meters per second squared and plus 0. Well, probably didn't need to show all this work, but your resultant acceleration is 6 meters per second because there is no vertical component at all here. So the acceleration is along the x-axis only. So along the positive x-axis. We don't even really need to find the vector. I'm sure you can go ahead and find the angle. It's going to be 0 degrees if you were to solve it out using trigonometry. But so that's our net acceleration along the x-axis. There's only a horizontal acceleration. There is no acceleration along our y-axis. So remember that since we're now dealing with vectors along two-dimensional planes, we can break up a velocity into its horizontal velocity and vertical velocity. We can break up the acceleration into its horizontal component and vertical component. And we can obviously break up the position vector. If we were to draw a position vector from here to here, we can break that up into the horizontal displacement and the vertical displacement. And the reason we need to do that is because if the object only accelerates along one axis, then what happens horizontally will be independent of what happens vertically. And you'll see that as we discuss projectile motion.